Alright, so in this session we're solving Chemistry 1010 tutorial sheet 1 2026. So we are solving all these questions. Now as we are solving these questions, you can hit the like button and you can also subscribe to our channel. So basically this is how we're going to go. Let's start with the first question. We are told to evaluate each of the following and write the answer to the appropriate number of significant figures. So our A, they've given us those figures. Okay, so now we are adding all those numbers. So we've got 212.2 plus 26.7 plus 40209. Now when I add those numbers on my end, I'm getting 641.09. Now you can be pausing the video to just try out these numbers, okay, so that you confirm. Okay, so I'm finding that now they're asking us to answer to the appropriate number of significant figures. So we have to first consider how many significant figures does this number have. Okay, for this one, let's consider the decimal places because it has one decimal place there. Then this one, it has one decimal place as well. Then the other one, it has two decimal places. Now you know that according to the rule of addition, the result must be reported to the least precise decimal place. And among these numbers, we're able to see that the least that we can have is one decimal place. So in this case, our answer has got two decimal places. So we're supposed to make sure that it has one decimal place. So in this case, we're going to have 641 point. Now this number is greater than 5. So we're going to add the 1. So you're going to have 641.1. So that would be the solution for A. Let's come to B. Okay, so we've got those numbers. We've got this to the, okay, then we've got a minus, then we've got that. Okay, so here we have to make sure that we solve what we have in the brackets first. So this is, if I simplify that, 1.646 times 10 to the power 3. So I'm getting 1646. That is what I have. Minus, okay, then I've got 2.18 multiplied by 10 to the power 2. 10 to the power 2, that is just 100. It means the point is just moving 2 times. So here I'm just going to have 218. Then we've got a plus there. We've got 11.36. Then we're multiplying it by 10 to the power 4, which is like 10,000. Okay, so it means the point is going to move like 4 steps. Okay, so in this case, what are we going to like have? So 11.36. What does it give us? I'm going to have 11.3600. Okay, now here I have to be very careful because this is in brackets. Okay, so I have to make sure that I solve it independently. So there's a multiplication of 5.17 times 10 to the power negative 2. That gives me 0.0517. Okay, basically that. Now I'm going to have 1646 minus 218 plus, now when I multiply this in the brackets, I already have my 0.0517. I'm just multiplying it by 113600. So I'm getting 5873.12. Okay, now that I've got that, let me just now add these numbers. So I already have this figure on my calculator. I'm just adding 218 plus okay, so 1646 minus 218 plus 5873.12. I'm getting 7301.12. Okay, now let's go back to our rules. If we're going to look at this first one in this simplified form, which is a simplified version of this one, this simplified version is this one. Okay, now if we are going to consider this one, the first one, it has no decimal places. Okay, so this one, no decimal places. This one, no decimal places as well. But when we solved this one, it gave us 2 decimal places. This one gave us 2 decimal places. Okay, so it means if this one gave us 2 decimal places, our answer, we're going to get, according to the rule of addition and subtraction, we're going to get the one with the, the least precise. So let's say the least number of decimal places. In this case, the least precise is the one that has no decimal places. Okay, so in this case, our answer is just going to be, it's going to be 7301. Okay, without any decimal place, because these are the ones with the least. So basically that's how we solve B. Let's go to C. Okay, so C is not very much different. We are multiplying those numbers there. Okay, so let's start with which one? We know that if I've got 1912 multiplied by, this is 10,000. Okay, this is 10,000, and we've got 0.007. So it means the point is going to move 4 times, four steps. 1, 2, 3, 4. So I'm just going to have a 77 there. Okay, I'm going to have 77 there, and it's multiplying by the 1912. I'm getting 14724, like that. Okay, 147,224. Then I'm multiplying this same answer multiplied by this that we have. Okay, 3.12 multiplied by 10 to the power negative 3. Because it's negative 3, it means I'm moving now on the other side, three steps. Okay, so this will give us like 0.00312. Then I'm supposed to multiply these two numbers. What do I have? I already have my 0. That multiplied by 147,224. I'm getting 459.33. Okay, now this is what we have as the numerator. Now if I simplify the denominator, look at, is 4.18 times 10 to the power negative 4. Now negative 4, there's a 3 outside. The negative 4 is going to multiply with the 3. I'm going to have negative 12. Okay, so that is what we have. So I'm supposed to now punch this on the calculator. I just see what it gives me. Okay, so this is giving me 73.0, let's just times 10 to the power negative 12. Okay, negative 12. So let me just move the point a bit this side so that we have a point there. I'm just going to have 77.3 times 10 to the power negative 11. Okay, so basically this is what I have. I'm now going to divide it into the number that we're just from finding 10 to the power negative 11. So now I've got 459.33 divided by 7.3 times 10 to the power negative 11. I'm getting 6.29 times 10 to the power 12. Okay, so this is what we have. So I have to go back to our rules of significant figures. The first one, it has 4 significant figures. Okay, then the second one in its simplified version, or just like that, the second one, you're able to see that in its standard in its scientific notation or standard notation, we're able to see that this one, it has, so I'm saying this one is 4, this one, it is 2 significant figures. Then the other one, this one, it is 3 significant figures. Then the last one, this one is 3 significant figures. Now because we're multiplying, you know, according to the rule of multiplication, you get the one with the least number of significant figures. So in this case, our answer should have 2 significant figures. So this is our answer there. So now what do? We're just supposed to express this to 2 significant figures. It's going to be 6 point. We have a 2 there and we have a 9 following it. So in this case, we're going to add the 1 to the 2. We're going to have 6.3 times 10 to the power 12. So that is how we solve the first question. Let's come to question number 2. Which one is the greater, or which one is greater? So we've got all these answers there, or questions. Let's start with the first one. For A, we've got this one, 3245 micrograms. Then the other one is, okay. So basically micrograms and milligrams. So what do we then do? So for you to be able to achieve this, you are supposed to at least convert to the same unit. So you know that 1 milligram is equivalent to about 1000 micrograms. Okay, so that is the conversion unit that you're supposed to know. Now we're told, let's convert this one to micrograms. Okay, so we're converting this one to micrograms. We want to convert it to that number. We see what we're going to have. So I can put here 0.00515 milligram is equals to, I can put an x there if I want. Okay, so in this case, for us to find as the x, I'm going to have x, okay, x multiplied by 1 milligram. This would be just equals to what do we have, 0.00515 milligram multiplied by 1000 microgram. Okay, then I'm going to divide by 1 microgram on both sides, 1 microgram on both sides, like that, 1 milligram actually. Then this is going to divide, I'm just going to have my x as the 1 milligram, and the 1 milligram can cancel. Now I have my answer in milligram. Now because I'm multiplying by 1000, you are going to see that the point is going to move 3 steps to the right. So 1, 2, 3. Okay, so therefore my answer is going to be 5.15 micrograms. Okay, now the question will be for us to now compare. Okay, so this, is it greater than 3245? So able to see that the 3245, or the 3245 micrograms is greater. Okay, so in this case, the greater one, it is the 3, the one that starts with 3. So the one we are just from finding is less. So basically that's how we solve all these ones. Let's solve B as well. So for B, we are told that we've got 3257 milligrams. Okay, then the other one, it is in kgs. So we're supposed to also convert to the same unit. So in this case, what is the conversion unit between the two? Now you have to know that if you're going to look at 1 kg, okay, because here we're dealing with grams, and you know it can be kilograms, milligrams. So now if 1 kg itself is goes to 1, now a k in front is kilo. Kilo means 1,000. Okay, so I'm going to put 3 zeros there. Then grams. Okay, 1 kg is goes to 1,000 grams. Now if we're going to convert this again to milligrams, okay, so in this case milli is going to be 10 to the power -3. Okay, so in this case, if we're going to convert this to milligrams, therefore it's going to be, we're going to add 3 zeros again, 1 2 3. This is for the grams, then like that, this is milligrams. Okay, now if that is a conversion unit, we are converting our 3257 milligrams, okay, to that number that we have. Okay, so now what are we then going to do? So let's get let's get also the last one. In this case, let's convert the kgs to milligrams. Okay, this one we convert it to that. We see what we're going to have. Okay, now we've got 0.00047 5 kg. What is it going to give us in terms of milligrams? Okay, in terms of milligrams, I can put an X there. So allow me to rub this 1000, okay, because 1 kg will be equals to 1000 milligrams. Then what about this amount of kg? So it's a sum conversion. We're just going to have 1 kg multiplied by the X we're trying to find will be equals to, now we're multiplying 1 million multiplied by this figure. Okay, what are we going to have? Now able to see that the point is going to move 6 steps. So it's going to move 1 2 3 4 5 6. So able to see we're just going to have a normal number. So in this case we're going to have 475 kg. Now since we're multiplying with the milligram, I'm going to maintain the unit for now. Then we're going to divide by the kg on both sides, kg on both sides. Okay, therefore now our X will just be equals to the kg, and the kg can cancel. Therefore your answer is going to be 475 milligrams. Okay, now the question will be, you're trying now to compare this that you have and that. Okay, so able to see that this one is greater. Okay, so the first one is also greater for B. Let's come to C. Now for C, we're saying 981 cubic centimeters. Then the comparison, the one you're comparing it to is 0.25 liters. Okay, so you know that we're talking about volumes here. 1 cubic centimeter is equivalent to 1 mil, okay, or 1 milliliter. And then you have to understand again that 1000 mil is equivalent to 1 liter. Okay, so we are given 981. Okay, so what are we going to do? So since we're converting between centimeters and liters, so what is going to be our conversion unit? Let me just pick one of the different colors. So here I'm going to have 981 centimeter cubed will be equivalent to how many mils. Okay, if this is that is 9 centimeter cubed, if I try to convert to mils, what is going to be my my conversion unit? So it means let me convert it to liters. So our conversion unit is between 1000, okay, 1000 and the other one. So I can put X here. Okay, I can put X there. Now what I'm now going to have is that I'm going to have because 1 centimeter cubed is equivalent to 1 mil. So in this case I'm going to have 1000 X will be equals to 981 cubic centimeters multiplied by 1 liter. Okay, in this case I'm going to divide now by 1000 on both sides. In this case my X is going to give me, if I divide 981 divided by 1000, that will give me 0.981 liters. Okay, so this is centimeter cubed, this is centimeter cubed. Okay, this is centimeter cubed. So these ones are just going to cancel like that. That's also it's giving us those amount of liters. Now I didn't mention earlier that because you're able to see the conversion unit, 1 cubic centimeters is equals to 1 mil. Okay, so if you've got 1000 mil is equals to 1 liter, this also equates to 1000 cubic centimeters is also equals to 1 liter. Okay, that's why we have to use this conversion unit there. Okay, so we found that. Now we're supposed to compare. Okay, here we've got 0.981 liters and here we've got 0.25 liters, and when we compare the two, you're able to see that the one we're just from finding is one that is greater. So this one is greater than the one they've given us. Okay, basically that. Then for the last one, it's just about conversions between temperature and temperature in terms of kelvins and degrees Celsius. Now we're supposed to convert Celsius to Kelvin. Okay, so you know that a Kelvin, for you to find a Kelvin, it is the temperature that you have in degrees plus 273. Okay, so in this case we've got 105, so I've got 105 as my temperature in degrees Celsius. Okay, this, if we're going to find it in terms of Kelvin, it's just going to be the same 105. So the Kelvin temperature will be 105 degrees Celsius plus 273. Okay, in this case it's going to be 378 Kelvin. Now if it's 378 Kelvin and we compare, if this is equals to that, then on the other side we've got 373. So the one that we found is greater by about 5, right? About 5 kelvins. Okay, so that is the one that is greater. This is the greater one. We come to question number 3. Now we are told that the beakers shown below have different precisions. Okay, then label the amount of water in each of the 3 beakers to the correct number of significant figures. Then is it possible for each of the 3 beakers to contain the exact same amount of water? If no, why not? If yes, did you report the volumes are the same in part A? Explain. Then suppose you pour the water from these 3 beakers into one container, what would be the volume in the container reported to the correct number of significant figures? Okay, so this is very simple based on what you are seeing. Okay, you don't have to be very accurate or precise, but what are you seeing? Okay, so let's start with beaker number 1. We're trying to label the amount of water in each of these beakers. So if I'm going to call this one as beaker number 1, this one as beaker number 2, and this one as beaker number 3. Let's start with beaker number 1. Okay, so if you are going to look at the scale is, they've got 26, 27, 28. Okay, so the scale shows those mu's. Now so where is the water going to be? Okay, so this is 27, this is 26. I'm looking at it like it's around the mid, right? That is like 26.5 mu's. Okay, now 26.5 mu's, and if we look at all our figures, they have around two significant figures. This one has got 3, the one we've written. I'm still going to round it off. Okay, this will give me around 27 mu's. Okay, very important. Now the precision, if we're going to look at the precision, how precise are the values to each other, how close are these values to each other? So the precision between these values, you're able to see from 26 to 27 is 1 mu, 27 to 28 is also 1 mu. So the precision for this one, which I'm just going to write as P, it is about 1 mu to the nearest 1 mu. Okay, so basically that this, we've expressed it to two significant figures. Okay, we come to beaker number 2. So 20, 30, 40. So the difference in terms of precision, how the values are close to each other, is around to the nearest 10 mu's, right? So let me just write the precision in advance, around 10 mu's. Okay, now what about because the scale is showing 20, 30 and 40. Now the water level is around close to like 20.5, right? It's around 25 actually. Okay, around like 25. Now if it's like around 25, that can be a rounded figure, maybe even close to like 27. Okay, or maybe a rounded off figure. But in this case, let's get it like that. But if we're going to find the average between those ones, if I say 20 plus 30, that is a 50, plus 40, that is a 90. Okay, a 90 divided by 3, that is like around 30. Okay, so if it's around 30, I'm not going to write 27 or 25 because it's around this area. Okay, so I'm just going to round it off to say, okay, this is 30 mu's. Okay, now if that is 30 mu's, the precision you said is around 10 mu's. Okay, and that makes sense. Then in terms of significant figures, all of them have got one significant figure. So this one is 1, 1, 1. I'm just going to get just the same the way it is. Okay, basically that. Why I didn't want to go for a number like 25 again is because look at this one has got two significant figures. Okay, so it contradicts with everything that we are adding. So basically that's why I wanted a rounded off figure, and considering also the precision. Okay, and then if we're going to look at which other one? Beaker 3. If we look at beaker 3, that is 26.4, 26.5, 26.6. Now what is the precision there? How close are they? Okay, to the nearest what? These ones, if you're going to look at them, to the nearest about 0.1 mu, right? To the because it's like from this figure you added the 0.1, 0.1 and like that. Okay, now in terms of the number of significant figures, and what is the value there? We've got 26.4. It's around what? Okay, so the water level is at close to like the same 26.4. Okay, basically that it's close to that. I can't say it is maybe 26.5 5 is just very far away, okay? But it's very close, and I can say maybe it's 26 point I say 4, maybe 4.5. Look at the numbers that we have. We've got all of them have got 3 significant figures, so you don't want to add another number there. So it's around that area, around that number, okay? So I'm going to get 26.4. How many significant figures? This one I've gotten it to 3 significant figures, okay, based on what we have there. So you have to be very mindful on how you choose these answers. Okay, basically those are our answers. Then B is asking us, is it possible for each of the 3 beakers to contain the exact same number of water? If no, why no? If yes, did you report the volumes as the same as in part A? Explain. Okay, physically it is very possible. Yes, they could all contain the same actual number or the same volume of water. Whether it's big, okay, whether it's small, whether it's big, or maybe we're in the same range. Typically they can all have the same or the actual amount or volume of water. But now here is what is very important. Each beaker has a different level of precision. The reported values are not the same, okay? Basically this one, the precision is around like 1. This is how close your values are, okay? This other one is very precise. It's like around 0.1, okay? However, if this other one is, it tends to be like an outlier. It's very far away, if at all we are the true value, okay? So basically that. So the conclusion that we can just give is that the difference comes usually from these measurement resolutions, not really actually the actual water, because the other one is seeing it from the other end, the other one is seeing it from the other end. So overall, or in the nutshell, we can just say yes, they could contain the same actual volume, but the reported values differ because of precision. So that is very important. Then for C, suppose you pour the water from these 3 beakers into one container. What will be the volume in the container reported to the correct number of significant figures? Okay, so in this case, then what are we supposed to do? So we're just supposed to add these numbers that we have, and okay, let me not rub the my precise values. I'm going to have 27 plus 30 plus 26.4. Okay, what do I have? I'm getting 83.4 mils. Okay, that is what I have. Now the question would then be in terms of precision. Okay, looking at this one, it is to the nearest 1 mil. This one is the nearest 10 mils. This one is the nearest 0.1 mil. So someone would ask, which one is the least precise? Okay, which one is the least precise? Because for this, we're going to go with the least precise. Why we're going to the least precise? Because these measurements are rather different a bit, so we're going to consider them in terms of precision. Okay, so now this one is more precise than 10. The figures are just far away from each other. Okay, this one is more precise. It's the most precise actually. So this, how many significant figures does it have? It only has 1 significant figure. So it means also our final answer should have 1 significant figure. Okay, so that's what they want. In this case, it's going to be what? Okay, around what? Around you can write maybe around 83 mils, or even around 80, that figure. Okay, basically that. Then we come to question number 4. To determine the volume of sodium hydroxide, 3 students, Cleopatra, Joshua, and Eugene, made a set of measurements with the burette from 3 trial titrations. as in the table below. Okay, so for those who are going to continue with us on Monday, we're starting more we are starting part of our tuitions, so you can just join us. We're going to talk about titration in detail. Okay, of course you're going to learn it in class, okay, but that's the way we do it as well. So if the true volume needed to complete the reaction is 15.62 centimeters, which of the students would illustrate the following? Imprecise, inaccurate, precise but inaccurate data, precise and accurate data. Give a possible explanation as to why data can be imprecise or inaccurate. What is wrong with saying a set of measurements is imprecise but accurate? Okay, so for you to be able to know about all these ones, imprecise, inaccurate, we've also done a video on accuracy and precision, so you can also just check that one out. So here you have to first find for each case the true value. They've told us it is 15.62 centimeter cubed, so that will be our benchmark. It will be our standard reference point. Let me just mark it like that. Let's start with Cleopatra and her trials. So let me just write C. Hope we'll know that one. We've got trial number 1, trial number 2, and trial number 3, 4. So our figures are around 23, 17.23, 17.21, 17.26. Now the question would be, how precise is she? Okay, how close are the values to each other? So these values are very close to each other, right? So Cleopatra was precise. Okay, but in terms of accuracy, if you're going to look at this 17, it's very far away from the 15 there. Okay, the 15.62, it's very far, so she was inaccurate. Okay, so she was precise but inaccurate. Then we come to Joshua. Joshua is around 18.21, 17.61, 15.42. Okay, those are the volumes that Joshua collected. Now you look at the spread, how close the values are to each other. You're able to see that these ones are very wide apart. Okay, the spread is very wide, so Joshua was imprecise. But when we comment on accuracy, we're able to see that it is inaccurate. Inaccurate. Okay, imprecise, inaccurate. So basically that. Now let me just even comment on this one. The second question B is asking us, give a possible explanation as to why data can be imprecise. Give a possible explanation as to why data can be imprecise or inaccurate. No, not this one, but the last one. What is wrong with saying a set of measurements is imprecise but accurate? So we're going to consider this one when we start talking about that. Okay, then we talk about who is this? Eugene. I'm going to write Eugene here. Now Eugene, we are saying those are the values: 15.67, 64, 15.61, 15.63. So for Eugene, looking at his trials, the values are very close to each other. Eugene was precise. When you comment on accuracy, look at the true value. It's about 15.62. Okay, although there is no accurate value there as the way it is, but they are very close to 62. Okay, to a decimal of 62. This one is 64, this one is 61, this one is 63. Very, very close. If we're going to find the average, it's going to be around the same true value, this one. So Eugene was accurate. Okay, not only was he precise, he was also accurate. Then we come to the last one, Natasha. We look at Natasha, 16, 16, 16, 31, 37, 34. Okay, so the values, if you are going to look at the values, all of them are in the range of 16. Natasha was precise. Okay, but to comment on accuracy, she was not accurate. Okay, I'll just say inaccurate. Okay, so basically those are the figures that they have. So we've commented based on precise and inaccurate data. Precise but inaccurate. We've done question number 1. We come to B. Give a possible explanation as to why data can be imprecise or inaccurate. Okay, why is it that the spread between the values can be very far away? Okay, like we can give an example, like which one? 18, the other one for Joshua, the other one was 15. Why is it that the spread can be very high to make the figures to be imprecise? So if you're going to look at precision, mostly it's going to be caused by poor technique. Okay, then sometimes the way you're just handling your instruments, okay, inconsistent handling techniques, or let's say handling of equipment. Okay, and then sometimes, mostly precision is also the error due to parallax. Okay, the error due to parallax. The meniscus, how are you looking at the meniscus? Okay, the surface at which the liquid is caving, also that can also can also affect that. Sometimes also just some random fluctuations can also cause imprecision. But if you are going to comment about inaccurate data as not getting the actual value, most of the time it's going to be caused by systematic errors. Okay, systematic errors. Like most of the time we're talking about those things that maybe the instruments themselves, like the burette itself is miscalibrated. Okay, sometimes also the solution itself is contaminated. Okay, or some incorrect reading of the scale. So basically those ones can also contribute to us having wrong answers. Then the last question is asking us, what is wrong with saying a set of measurement is imprecise? Okay, imprecise but accurate. So okay, it doesn't make sense, right? Because accuracy means values are close to the true value. Precision means values are close to each other. Now if data is imprecise, it means that the values are scattered. Okay, like we've seen, the values are scattered. Now if you're going to say, okay, this data is imprecise, meaning the values are very scattered, they cannot be very close to the true value, which is accurate. So if data is accurate, the values must cluster around the true value. So you can't say imprecise but accurate. That's why they're saying it is wrong. Therefore you cannot have scattered values that still consistently represent the true value. So it's contradictory. So what we can just conclude is that accuracy itself requires at least some degree of precision. That is very important. Then we come to question number 5, where say a non-SI unit of mass used in pharmaceutical work is the grain. Okay, non-SI unit of mass. Mass has a lot of units, kgs, kilograms. That's why they're saying a non-SI unit. So that is very important for us to understand. And that 15 grain is equivalent to around 1 gram. Okay, then an aspirin tablet contains 5 grain of aspirin. Then is it 155 pounds, and 1 pound is equivalent to about 0.454 kg. Athletic individual takes 2 aspirin tablets per day. Okay, so arthritis is just an inflammation. We're not talking about that. that is for medical students. What is the quantity of aspirin in 2 tablets expressed in milligrams? Okay. Then what is the dosage of the rate of aspirin expressed in milligrams per, okay. Then at the given rate of consumption aspirin, how many days would it, okay. So this is very, very simple. They've given us a non-SI unit, okay. They've told us the information that we are given is that 15 grains, which is GR, is equivalent to 1 gram. Now, in terms of milligrams, they were asked what is the quantity of aspirin in 2 tablets expressed in milligrams. Okay. Now, in milligrams, we said 1 gram is equivalent to about 1,000 milligram. Okay, because milli just means that 10 to the power negative 3. Now, each aspirin tablet, they've told us an aspirin tablet contains 5 grains of aspirin. So each aspirin tablet, I'm just going to write S80, each aspirin tablet is about 5 grain. Okay. Now the patient weight, we've been given that this patient has a weight of 155 there pounds. 155 pounds. Now if that is the weight, then they've given us a conversion there that 1 pound, okay, 1 pound, 1 lb is equals to 0.454 kg. Okay. Then this patient takes 2 tablets and takes 2 aspirin tablets per day. Okay. So each tablet contains 5 grains, but they take 2 tablets per day. Okay, 2 tablets per day. Let's just write it like that. Okay. Then let's now answer these questions. What is the quantity of aspirin in 2 tablets? Quantity of aspirin in 2 tablets. So supposed to convert the grains, what we have in grains, to grams. Okay. We've got 15 grains, and that is equals to like 1 gram. So in this case, what are we going to do? So I'm going to have my 15 grain. Okay. The conversion unit, it is 15 grain is equivalent to 1 gram. Okay. We know those conversion units, and I'm writing like that because you've done units and measurement. So the grain and the grain are going to cancel in this case. Then what then are we then going to have? Okay. So if that is the case, then what is our answer? Actually, I'm not even supposed to do it like that. We're just dividing 1 divided by 15 itself. Okay, because it's already a unit of conversion on its own. So in this case, what are we going to have? 1 divided by 15, we're going to have 0.333 gram per tablet. Okay. Okay. Now we're supposed now to convert these grams of the ones that we have per tablet. We're supposed to convert them to milligrams because they want our answer to be in milligrams. So what we now have is again the conversion unit. 1 gram is equal, so we've got this same answer that we have. What am I now going to do? The conversion unit is 1,000. Okay, so I'm going to have this is going to be multiplied by the gram. Okay, so I'm going to have 1 gram this would be equivalent to 1000 milligram. That is the conversion unit. So the gram and the gram can cancel. Therefore, I'm just multiplying 0.33 multiplied by 1000. So in this case, it's going to take us back. I'm just going to have 3333 milligrams per tablet. Okay, that is per tablet. Now this person is taking 2 tablets. What is the quantity of aspirin in 2 tablets? So in this case, our answer that we have was supposed to multiply it by 2. Okay, so we're going to multiply this figure by 2. So I'm just going to have what? I'm going to have about 60 milligrams. Okay, so that would be the answer for the first one. Okay, now we have a lot of things here. What is the dosage rate of aspirin expressed in milligrams of aspirin per kilogram of the body mass? Okay, so the dosage rate in milligrams per kg body mass. Now we've been given, every time we're talking about kgs here, we're talking about per kilogram, we're talking about the mass, right? So we have to convert the patient weight to kg, because we've been given it in pounds. Okay, and what is that? And the conversion unit is there, 155 pounds. They weigh like 155 pounds. So what then is going to be our answer? So I'm just going to say x here. Okay, I'm just going to put x, then I cross multiply. I'm going to have 1 lb multiplied by x will be equals to 15 or 155 lb multiplied by 0.454 kg. Okay, then I'm going to divide by 1 lb on both sides, 1 lb on both sides. Then x then will just be equals to, the lb and the lb are going to cancel. Then 155 multiplied by 0.454 in kgs. What then am I going to have? Okay, when I multiply that, I'm getting 70.4 kgs. Okay, so that is what I have in terms of that. Now the dosage rate, this person is taking 666 milligrams of these tablets. So now I'm supposed to now divide that, because I'm trying to find the rate. How many milligrams does she take in terms of the weight, if it's a she, by the way, or if it's a male? How many does he take if it's if they are around this weight? Okay, so in this case we've got 666 milligrams divided by 70.4 kilograms, okay, kgs. And when I divide that, what am I going to have? 666 divided by 70.4 kg. I'm just going to have 9.46. This will be milligram per kg. Okay, milligram per kg. Now you can round it off, you can even round it off to 2 significant figures. I'm going to have 9.5 milligrams per kg. Okay, so that is what I have there. Okay, let me just wrap this part. Okay, so the dosage rate, we said, okay, the first one we said it is 666 milligrams. Okay, then this one, the dosage rate, just from finding, is a 9.5 milligram per milligram per kg. Then C, we're saying at the given rate of consumption of the aspirin tablet, how many days would it take to consume about 1 kg of aspirin? 1 kg. Okay, so we're supposed to convert this 1 kg to first, this is 1 kg. We're supposed to convert it to milligrams, because everything that we've been given is in milligrams. Okay, now you know that 1 kg we said is about 1000 grams. 1,000 grams is like 1 million milligrams. Okay, so the conversion unit here is what? 1 kg is equivalent to about 1 million grams. Okay, 1 million milligrams actually. Okay, basically that. Now this person has been taking 600 milligrams of a tablet. Okay, then what to find out that what did we get? Milligrams per kg in terms of days. So per day they take 2 tablets, and those 2 tablets is 60 milligrams. So this is per day. Okay, now in terms of time now to consume at that rate. Okay, and we found that the conversion unit is that 1 kg is equals to 1000 milligrams. So in this case, what then are we going to do? So we're going to have a scenario where we have this. I'm going to multiply it by, okay, since they've said 1 kg, here we have to be very careful. They've said 1 kg of aspirin. 1 kg of aspirin is about 1 million of milligram. 1 million milligrams. So I'm going to write it just the way it is. 1 million milligrams. We are multiplying this by what they consume per day. Okay, so in this case, what they consume per day, it is 660 milligram. Then day is there. Okay, per day. So the milligram and the milligram are going to cancel. Then we can now divide, 10,000 divided by 60. Is it 10,000? No, I think that is 100,000. Yeah, 100,000 divided by 66. We're getting 150, around 00 days. Okay, so basically that 1,500 days rounded off to like those significant figures. So basically that's what it means, and that's how we solve this one. Then for question number 6, complete the following table. What minimum amount of information is required to completely characterize an atom or ion? Hint, not all arrows can be completed. Okay, so they've given you a hint. Even if you look at everything in this table, it's not everything that you can complete. Number 1. Number 2, the question is what minimum amount of information is required to completely characterize an atom or ion? Okay, so that is the first question that we should know. Number 1, for you to completely, okay, the minimum information that you need to characterize an atom or ion. Number 1, you have to know the element name. Okay, the element name or the symbol. Okay, the symbol of that element. Mostly this one, we're talking about the proton number is going to help you, which we usually call the atomic number. Okay, the proton number. Then you're supposed to know the mass number of that element. Here we're talking about together with the neutrons. Okay, then you're supposed to know also the charge. Okay, the electrons. So these 3, they are going to help us, to then talk about fill this table completely. Those are the 3 things that they need. Now, proton number or atomic number. Proton number. This one defines the element itself. It's the atomic number. Now, when we talk about neutrons for them, we're talking about the mass number minus the proton number. Okay. Then electrons. In a neutral atom, electrons are going to have the same number of. They are going to be equal to the number of protons. Okay. Then the mass number is just going to be what you have as the protons plus the neutrons. Then the net charge, mostly the protons minus the electrons, because these are the only 2 which are charged. So basically this is the information that we really need to just fully put this table into to let's analyze the first one. So sodium, they've told us it has a mass number of 23 there. Then what we see down as 11, that is the atomic number. So the proton number, it is 23. Okay, then they've told us the mass number in this case for sodium, it is 23. So that is there. Okay, now this 23, the number of neutrons, we're saying it is 11. Okay, it is 11. So now for it to be 11 plus 11, that is like 22. Okay, where is that proton? Okay, so I think there was a mistake on the first one. Okay, basically that. Why? Because we can't have a net charge. We said we can't have a net charge of 0. If at all we have the protons are this is 11, then the electrons are 12. So we are seeing an excess there. We can't have that scenario. So the first one was not really complete. Okay, we come to lead. PB is lead. Okay, now your PB, we're going to write lead there. Okay, now they've given us the number of neutrons, they've given us the mass number. Okay, so first to find the number of protons, we're supposed to subtract 206 minus 126 for lead. Okay, I'm going to find 82. Okay, now the mass number they've already given us, which is 206. I'm just going to put it in advance, 206. Okay, then the number of electrons provided this lead, the number of electrons in this case is going to be what? It's going to be the same as the number of neutrons, as the number of protons. So 82. That's the scenario we're supposed to have here as well, for us to have a charge of 0. Okay, that's why I'm saying that is wrong. So here we're going to have 0 charge. Okay, that is lead. We come to silicon. Silicon, the symbol, they want us to put the symbol here, it's Si. Okay, now it means Si, you have to check for it. They've said the number of electrons, the number of neutrons is 14, then everything is blank. Now for silicon, we have to be very careful. It depends on the isotope you're talking about, because the 14 neutrons, they are for silicon 28. Okay, so that's for silicon 28. So the mass number, if it's silicon 28, we're going to have 28 there. Okay, then the number of protons from that, 28 minus 14, then what are we going to have? We're going to have 14. Then the number of electrons is going to be 14. Then we're going to have a charge of 0 there. Then these other elements, there's 31 here as the proton number, and the neutron is 38. Now when we add 31 plus 38, what do we have as a mass number? 69. So I'm going to have 69 here. Now because I have a charge of 3 there, 3 plus, what then is the number of electrons? Okay, what is the number of electrons? Protons, we got 31. We've got a charge of 31 plus. Okay, 31 plus. So in this case, what then are we going to have? We're going to have 28, right? 28 electrons. The difference between them is is 3 electrons, which is that, okay? Because we've lost 3 electrons. That's what the 3 plus mean. We've lost 3 electrons. So instead of us also having 31 electrons, we have 28 electrons there. Okay, then what is the symbol and the element? So the symbol for this one, we don't know, okay? We're just going to say Zi. Well, I'm just going to say Zd. We found another element, which is Zd is equals to 31. Okay, it has a number of protons of 31. Then, of course, we're just going to say it's unknown. You can check that on the periodic table if you're going to find anything like that. Then, also, you are going to do for the second one, for the third one. Let's do for manganese. Manganese, I'm going for it because of this ion there. Now, if we're going to look at manganese, it also depends on the isotope. So, for this one, the one they've given us manganese 30, okay? The 30 for the 30 neutrons. This is for manganese 55, okay? Now, manganese 55, the mass number, I'm just going to put it in advance. Mass number is 55. Okay. Then from that 55, we subtract a 30. We're going to have a 25 of protons. Okay. Then for electrons, we have to be very careful here. This manganese has lost 2 electrons. Okay. So from the 25, we're going to subtract. We're going to have 23 electrons. Then in terms of, we're saying this is manganese, so I can write the name manganese. Okay. So basically, this is how you fill all this table and the concepts. Basically, it's not very hard. Then we come to question number 7. The stable isotopes of iron are, those are the isotopes. 4 of them, 54, 56, 57, 58. Then the mass spectrometer of ion looks alike. Okay, that is a mass spectrometer. Use the data in the mass spectrometer to estimate the average atomic mass of ion and compare it to the value given in the periodic table. So it means you have to go back to the periodic table and find out what value is there. Okay, so basically what then is the value of manganese on the periodic table of what's this ion. Okay, the periodic table value for ion is about, okay, it's about 55.85 atomic mass unit. So now it depends on the periodic table that you're using, but it should be around that. Okay, now let's solve this question. Use the data in the mass spectrometer to estimate the average atomic mass. So we're trying to find the average atomic mass. So what percentages are we given for these ones? We've got 54, we've got 56, 57, 58. Okay, let's start with 54. 54, we are given that it has a percentage of 5.85. Okay, so the green bars, the one that are very prominent, these are the percentages. So 58 there, then 56 we've got is about 91, then the other one is 2.12, then the other one is 0.28. So what we're going to do is that we're going to convert all these percentages to decimals. Okay, so this 5.85 in terms of a decimal, it just means I'm supposed to divide all of them by 100. Okay, so this is going to give me 0.0585. Then for the one with 91, it's going to give me 0.9175. Then the one for 2 is going to give me 0.0212. Then the one for 0.28%, 0.28 divided by 100, I'm going to have 0.0028. Okay, so those are the percentages that we have. Then we're going to multiply each isotope's mass by its fraction. Okay, so basically you remember the formula, right? AI, atomic mass unit, multiplied by the percentage abundance. The percentage abundance is what we're just from finding. These ones that I'm dividing, okay, this is what if we say 58.85%, that is the percentage. And when we divide, we have to divide so that we get these decimals. Then the answers that you get, you're now multiplying it by the atomic mass unit. Okay, the masses now for these compounds. So the first one, it is, we've been told that it's 54, it's ion 54. So I'm multiplying it by its percentage abundance, which was 0.585. Okay, what does this one give us? It gives us 3.16. Then we come to 56, the one that has a mass of 56. So 56, its percentage abundance was 91 something. 91 something, it gave us that. So in this case, multiplied by 0.9175. 56 multiplied by 0.9175. So this one I'm getting 51.38. Okay. Then we come to the last two. We've got ion 57. This is multiplied by, what did we find as a 57? It has a percentage of that. Okay, that is 0.0212. Okay, so when we multiply those ones, 57 multiplied by 0.0212, I'm getting 121. Then I come to the last one, which is 58. This is multiplied by 0.0028. So 58 multiplied by 0.0028. So I'm getting 0.16. So basically these are the figures that I have. Now for me to find and compare, I can only compare if I find the average of all these isotopes, because that's what atomic mass unit is about. You're finding the masses of each isotope, then you find the average. So we're going to have 3.16. So 3.16 plus 51.38 plus 1.21 plus 0.16. Let's see what we're getting. So 3.16 plus 5.38 plus 1.21 plus 0.16. So I'm getting 5.91. Okay, so that is what I have. Now we have to compare this with what we have on the periodic table. So the calculated that we've calculated, this is atomic mass unit that we've just calculated, is 55.91. Then the one that is on the periodic table, it's about 55.85. Okay, so basically we are around the same, or around the same value. It's still correct when it's, you don't have to be very accurate, but it's around that figure, and this is correct. Then we come to question number 8. We are told that the three naturally occurring isotopes of potassium are those ones. We've got 39, we've got potassium 40, and 41. Then the percentage natural abundances of potassium and potassium 39 and potassium 41 are these respectively. Okay, so the first one is for that one, the second one is for 41. Okay, then determine the isotopic mass of potassium 41. Okay, now I think we haven't been given anything about 41. We've just been told, or we've just been given the percentage abundance. Okay, so here what do we now do? Okay, let's look at the isotopes that we have. We got 39, potassium 39. I'm just going to write it as 39K. Okay, the mass that we've been given for 39, it's 38.963 0.707 units. Okay, then the abundance, we've been given that it's 93.2581%. okay, then for 40 we've been given that it is the mass is 39.963999 units. Then its percentage abundance is unknown. Okay, this one is unknown. We haven't been given for 40, we just been given for 39 and 41. Okay, so here I'm just going to put unknown, we don't know. Then when we come to 41, potassium 41, what do we have as atomic mass unit? We don't know. We've not been given. We've only been given for 39 and 41. Then what about its percentage abundance? We've been given that it is 6.7302%. Okay, so this data, when it's written nicely, it's going to help us to know what we're supposed to do. Now, what is the rule? The weighted average atomic mass of potassium must always be equal to the periodic table value. Okay, now potassium on the periodic table is around what value? Around 39.0983 units. Okay, that is potassium. Your kalium. So basically we're going to keep this figure there. It's going to help us for comparison. Now we're supposed to now calculate this. We're supposed to first find the missing abundance of 40. This 40 as what is the abundance. Okay, now you know that the abundance in this case is going to be what? Total abundance is 100%, right? Everything is around 100%. So the mass for the 40K in terms of abundance, I'm just going to write abundance will be equals to what we have, 100 minus the 2 that we have. We've got 93.2581. Then the other abundance is 6.767%, 0.32. Okay, so I'm moving 93% and 6.7% to find the other abundance. So in this case I've got 100 minus 93.2581 plus 6.7302. I'm going to get 0.00117%. It's a very, very small number. Okay, so if we're going to write this one as a fraction, it's just about around in terms of percentage. Okay, just remove the percent there. Okay, so that is what we have. Then if we're going to now calculate the average, okay, the average weight will be the fraction that we have multiplied by the mass for each isotope. So in this case, what then is where can I write? Okay, even just the same down. Okay, so let's start with the one that gave us 98%. So you know that the same formula that was just from taking AI multiplied by Fi. This is the atomic mass unit, then the percentage abundance. The percentage abundance, we're going to convert it in advance. We're going to be dividing all these answers, these percentages by 100. Okay, so that we just multiply what we have with the atomic mass unit. The masses we've already been given for some, not all of them. So in this case, let's start with the first one. The first one is 38. That is for potassium 39. That is 38.963707. Okay, now we're multiplying this by this percentage abundance, which is 93.2581 divided by 100. Okay, that will give me 0.9322 2581. Okay, I'm going to put this one in brackets. Then I'm supposed to find the other one. The second one, the second one is what? Okay, so one that was just from calculating its mass. We've been given that it's already 39.963999 plus its percentage abundance, one that was just from calculating. Okay, it is about 0.000117. Okay, plus the last one. The last one, it has a mass of what? Okay, we've only been given, because we don't know its mass. Okay, but we've only been given this percentage abundance. So let's just calculate this percentage abundance. That is about 0. If I divide by 100, I'm going to have 0.067302 plus the percentage. Okay, I'm just going to write it as maybe M2. Okay, any letter I can choose is still fine. Or maybe for us not to be confused, let me just say M41, because it's potassium 41, the atomic mass of potassium 41. Then what do we then do? All this should give us that figure, because this is a total mass after we find the average. Okay, so it means it's an equation. Okay, so we're supposed to solve everything and we equate it to that. So let's just now solve. Okay, so I'm going to write what we are getting. We're supposed to get 39.0983, just the way it is on the periodic table for potassium. Then what do we have? I'm going to multiply 38, this what I have there. So 38.963707 multiplied by 0.932581, I'm getting 36.34 plus. I come to this other figure. So that is 39.963999 plus, is it plus? It's multiplication actually. What was I writing? Multiplied by 0.0000117. Okay, here I have to be very, very careful. I'm finding 0.0047 plus. Okay, so this one again we're also multiplying. So this one we can't even, we're just going to write it the way it is, because we don't know what the M41. Okay, basically this is what we have. So we're just supposed to now what, add these ones and take them to the other side, then we divide it by this. Okay, so what then do we have? We're going to have 39. I'm going to write my 39.0983. This I'm going to subtract what I'm going to have. I've got 36.34 plus 0.0047. When I add those ones, they're giving me 36.3447. This will be equals to what has remained, 0.067302 multiplied by M41. Okay, then we're just supposed to now solve that part. When I subtract 39.0983 minus 36.3447, so I'm getting 2.7. So this is 2.7536. This is equals to 0.067302 multiplied by M41. Okay, for us to find now the M49, I'm just going to divide by 0. This term number on both sides. So this is 2.7536 divided by 0.067302. I'm getting 40.9. So that is 40.9 units. Okay, that is what we have as the isotopic mass of potassium 41. Okay, so basically that is how we solve this type of equation. We come to question number 9. We're told what are the percentage natural abundance of two naturally occurring isotopes of boron. We've got 10 and 11. These isotopes have masses of 10 and 11 units respectively. Now we're told to find the percentage natural abundances. Okay, so we have to first go on the periodic table. What is the average atomic mass just from the periodic table? So boron on the periodic table is about 10.81 units. Okay, now we need to find the natural abundances. So we're going to get the average, the formula. Okay, we can let these let's say we let x to be. From that percentage you have a fraction. Let's say the fraction of 10b. Okay, boron 10b. Then the other one, because it's a percentage, we're going to let another one. It will be x minus from that. It will be, let's say, 1 from that percentage will be equals to the fraction of 11b. Okay, it's like you're getting from 100%. Okay, then from that 100%, 1 is going to be just the way it is. If we choose it to be x, it's fine. But the other one is going to be that what we have, which is 100%, minus the x. So if I choose any number like 1 minus x, that will represent the other one. Okay, so that's SAS math. Okay, so that is what we have. Now the weighted average, what are we now going to have? We're going to get the one for the boron, the one for boron on the periodic table, which is 10.81 units. This will be equals to what we have as the first one for the percentage abundance for the first one. Okay, which is x. We've let it to be x multiplied by the atomic mass unit. The same formula, AI Fi. Okay, the atomic mass unit, the one that you see there on top of this one has 11, this one has 10. Okay, then of course, but they've already given us, these are the ones we should use. Okay, then the percentage abundance, okay, which we're trying to find. So the other one, we've put it to be x. Okay, then its atomic mass unit for the first one, the one we've put as x, which is 10b. We've put that also that its atomic mass is 10.012937. Okay, then the other one, its percentage abundance, we've decided to be 1 minus x. Okay, 1 minus x. So this one is going to be we're going to multiply this one by, we're going to multiply it by its by what? It's we have 11.009305 units. Okay, basically you are able to say this is an equation we just need to solve. 10.81, this will be equals to, okay, so it's just a matter of calculations there. Okay, here I'm going to have 10.012937x plus, when I distribute this one, I'm going to have 11.009305 minus 11.009305x. Okay, I've multiplied by the 11 with everything that is in the brackets. Okay, basically that. Then what do we now do? Just as a normal equation, we put the like terms together. Okay, so in this case, I'm going to have 10.81 is equals to, here I've got 10, this one has x, this one also has x, and they're subtracting. Okay, there's a minus there, so I'm supposed to subtract the two. So I've got 10 minus 10.012937 minus 11.009305. Okay, I'm getting around negative 0.996368x plus what has remained. Okay, what has remained? We've remained with 11.009305. Okay, then what do we now do? I'm supposed to take the 11 to the other side. Okay, the 11, I take it to the other side. It means it's going to subtract from this number. So I'm just supposed to subtract 10.81 minus 11.009305. I'm getting negative 0.199305. So this will be equals to negative 0.996368x. So for us to remain with our x, I'm just supposed to divide the two, right? So I'm going to have a positive number because all of them are negative. So I'm dividing 0.199305 divided by 0.996368. So I'm getting x to be 0.2. Okay, that is the percentage of this one. The one we let the percentage of 10 be, we have to let the percentage of 10 be to be x. So, and we found that the percentage is 0.2. 0.2 in terms of percentage is what? It's 20%, right? Now, if 0.2 is 20%, what about for B? For B, it is what we have as 100%, which 100% can be equivalent to 1, right? That's the highest you can have. So, it is 1. So, that is like 100% minus x, which is 20, right? 100 minus 20, that is 80. Okay, so for B, it's 80%. So, basically, that is how you solve this one. We come to question number 10. Indicate which of the following quantities contains the greatest number of atoms. Okay, so explain your reasoning. So, okay, these are very, very simple questions on more calculations. So, given options that we have, we've got, let's just write them down. The first one, it is 6.022 times 10 to the power 23. We're saying this is what? Atoms. Okay. Then we come to, I think that's nickel. Then we come to the second one, it is 1.78 moles of nitrogen. Okay. Then we've got the third one is 52 grams of chromium. Then the fourth one is 10 cubic centimeters of iron. Then we've been given its density there, which is density is equals to 7.86 grams per cubic centimeters. Okay, so then how do we solve these ones? So we have to remember that if we're going to look at the first one, this one, for nickel, that number there, you're able to see that that is Avogadro's number, right? Then for us to be able to indicate, to to compare which one has the greatest number of atoms, first we have to convert everything to moles, okay? Because you know that the number of particles or the number of atoms. So if you haven't read, if you are still finding challenges with the more concept and the stoichiometry, please watch our video. Just type stoichiometry Novastone Academy. You're going to find a video where I explained everything from scratch to, to the bigger concepts. So the number of atoms, or what we call the number of particles, I think the best way that I can use is the number of particles. Of course, they've told us to find the number of atoms, but just for the formula's sake, I'm just going the number of particles. These particles can be atoms, these particles can be ions, these particles can be molecules. Okay, so this is going to be found by the number of moles, okay, the number of moles that you are given multiplied by the Avogadro's number. The Avogadro's number, I'm just going to represent it as Na. Okay, that is the formula. So our target is for us to find all the number of moles for these ones. Then those number of moles multiplied by the Avogadro's constant. So let's start with the first one. How many moles can we have for nickel? Now, by definition, we said that exactly 1 mole of, 1 mole is equivalent to the Avogadro's number. So in this case, this one only has 1 mole, okay? That is nickel. More atoms of nickel. We come to nitrogen. Nitrogen, they've given us 1.78 moles. Okay, now here we have to be very careful because they've given us 1.78 moles of nitrogen. Nitrogen is a diatomic molecule, okay? So in this case, we're going to get the 1.78 moles that they've given us multiplied by 2. When you multiply by 2, we're going to have 3.56 more atoms. So here you have to be very, very careful. I think that's where the major is going to come from. Then we've got 52 grams of chromium. So the molar mass for chromium, itself is around 52 grams per mole. Okay, now you know that for you to find the number of moles is equals to mass over molar mass. Okay, now that we've been given a mass of 52 itself, so we're going to have 52 grams. So 52 grams divided by 52 grams per mole. So the gram and the gram are going to cancel. We're just going to have 52 divided by 2. 52 divided by 52, that is 1 mole. So we have 1 mole of chromium. Then we come to the last one, this one for density. We've been given a density of 7.86 grams per cubic centimeters. Now you know that mass, if density is equals to mass over volume, mass will be equals to density times volume. Okay, in this case the density is 7.86 multiplied by, I'm going to ignore the units from now, then multiplied by the volume. The volume in this case we've been given is what? 10 cubic centimeters. Okay, so that is 10. So we're going to multiply the 2. You know that the point is just going to move one step, so I'm going to have 78.6 grams. Okay, now from these grams, now we're supposed to now find the number of moles, and the number of moles is equals to mass over molar mass. So this same mass divided by the molar mass for iron. The molar mass for iron is about 55. So this is divided by 55.85. Okay. Therefore, to be the number of moles for this one, 78.6 divided by 55.85. I'm getting 1.41. So this will be the mole of moles of iron, 1.41. Okay, so that is what we have as a number of moles. Now if we're going to compare these ones, okay, explain your reasoning. Indicate which of the following contains the greatest number of atoms. Okay, the greatest number of atoms. So these are the moles of atoms that we have. So if you can find the number of atoms, but still you're just multiplying by the same number, so it's not going to change a lot. So what do I mean? If I multiply everything by 10 throughout, you haven't changed anything. Okay, unless if I was just So this is what I mean. This will find one more. We're going to multiply it by, if we multiply this by 10, I've just increased everything by 10. I've just increased everything by 10. It's not going to change anything. So if I multiply everything by the Avogadro's number, I've just changed the figures to a higher figure, which is, so even just from here we're able to compare. This has got one more. This has got 3.5. This has got 1. This has got 1.4. Okay, so which one has the greatest indicator show that contains the greatest number of atoms? So the one that contains the greatest number of atoms, we're able to see that it is that this one which has 1.78 moles of nitrogen. Okay, it's the one that has the greatest because it gave us about 3.56 moles of atoms. So basically that. Then we come to question number 11. Iron is biologically important in the transport of oxygen by red blood cells from the lungs to the various organs of the body. In the blood of an adult human, there are approximately 2.69 times 10 to the power 13 red blood cells, with a total of 2.9 grams of iron. On the average, how many iron atoms are present in each red blood cell? On average, how many atoms, okay, are present in each red blood cell? So what did we say, how we find the number of atoms? Okay, we talked about how we find the number of atoms. What you have as the number of moles to multiply by the Avogadro's number. So we're supposed to find the number of moles for this question. So we've been told, so what do we have as the let's find the moles. The moles of this iron will be equals to the mass over the its molar mass. The mass that we've been given, we've been told that it is 2.9 grams of iron. Okay, so in this case I'm going to have 2.9 grams of iron divided by the molar mass of iron. We said it's about 55.85 grams per mole. So what then do we have? The gram and the gram are going to cancel. Therefore 2.9 divided by 5.85, I'm getting 0.0519. This will be moles of iron. Okay, we found the number of moles for iron. Then we're supposed now to convert these moles to atoms, and we said the formula is just simple. If you are finding the number of atoms or particles, it's just going to be the number of moles that you have multiplied by the Avogadro's number. So in this case, the number of moles we found that is 0.0519 moles multiplied by the Avogadro's number, which is about 6.022 times 10 to the power 23. This will be atoms per mole. Okay, so the mole and the mole are going to divide. Therefore, we're just multiplying. I already have the 0.0519, so I'm multiplying it by 6.022 times 10 to the power 23. I'm getting 3.12 times 10 to the power 22 atoms. Okay, so this is what we have as the number of atoms. Now the question is very clear here. On the average, how many iron atoms are present in each red blood cell? Then what other information have we been given? In the blood of an adult human, there are about 2.69 times 10 to the power 23 red blood cells. Then I'm trying to find the how many iron atoms are present in each of them. Okay, in each of them, because this is a sum up of all of them. Approximately, those are what you can have, 2.69 when you add all of them. But now I'm trying to find how many are present in each. Okay, so because we're trying to find in each, we're going to now divide the two. Okay, so I'm going to divide the same answer that we're just from finding. So I'm going to divide the same answer that we're from finding. Okay, so this one I'm going to divide it by the number of red blood cells, which is 2.69. Okay, so the number of red blood cells, which is 1 to the power 13. Okay, 10 to the power 13. This is red blood cell. So we're trying to find the number of atoms present in each. So if it's in each, to be atoms per red blood cell. So in this case, what are we going to have? So 3.12 times 10 to the power 22 divided by 2.69 times 10 to the power 13. I'm getting 1.16 times 10 to the power 9 atoms per RBC, red blood cell. So basically that would be our final answer. So we come to question number 12. Medical experts generally believe a level of 30 micrograms lead per deciliter of blood poses a significant health risk. Then they've given us 1 deciliter is equals to about 0.1 liter. Express this level in the unit mole per lead, more lead per liter blood as the number of lead atoms per mil. Okay, so basically we're just doing unit conversions, and we've done a lot of them. Now we're converting. Let's start with the first one. More in the unit mole of lead per liter. Okay, so now we've been given that 1 deciliter is equals to 0.1 liter. Then what do we have? This is 30 micrograms of lead. Okay, now this 30 micrograms of lead in terms of micrograms per liter, what is it going to be first of all? Okay, so what do we then do if we want to convert this one to per liter? Okay, so what then do we do if I put x here? Okay, so you're going to realize we've been doing so much of these conversions, so it's just going to be 30 micrograms. It's going to be divided by the 0.1 liters. Okay, so that we find, or we're going to find about 30 divided by 0.1, that is 300 micrograms per liter. Okay, so that is what we have. Then we're going to convert our micrograms to grams. Okay, micrograms to grams. So in this case, then what are we going to have? We've got 30 micrograms. Actually, we've got 300 micrograms. 300 micrograms. Okay, for us to convert it to grams, you know that this would be the 300 itself multiplied by micro means 10 to the power negative 6, right? Grams. Okay, so basically that. Then when we multiply the two, 300 multiplied by 10 to the power negative 6, I'm going to have 3 times 10 to the power negative 4 grams. Okay, now we're converting grams to moles. So how do we now convert? So you know that the number of moles is equals to mass over molar mass. In this case, we've been given the mass. It's 3 times 10. So it's 3 times 10 to the power negative 4 grams over the molar mass for lead or lead. It is 207.2 grams per mole. Then the gram and the gram are going to cancel. Then you divide the two. I already have the 3 times 10 to the power negative 4. I'm just dividing it by 2.0207.2. So I'm getting 1.45 times 10 to the power negative 6 mole per per liter. So that is what I have in terms of moles per liter. Okay, so I've converted these micrograms to grams. Okay, then those grams we've converted them to moles. That's why I was saying mole per, there was a liter here, mole per liter, meaning we've converted that lead to mole per liter. That's how you do that one. We come to B. We are asked to as the number of lead atoms per ml of blood. Okay, per ml of blood. I think we're going to, for this one, our answer is going to apply. So atoms, the number of atoms. You know, the number of atoms, you said you're getting the number of moles. In this case, it's 1.45, the one you just from finding. Negative 9. Okay. Not really. First, let's calculate something here. There are mules here. I didn't pay attention for that. So there are mules. So we have to be very careful here. Since there are mules, we know that 1 liter is equals to about 1,000 ml. Okay. So if we got 1.45, the answer was that was just from finding mole per liter. Okay, for us to convert this liter to the ml that they want, it means we're supposed to divide by 1,000. Okay, 1,000 mls. Okay, in this case liters, okay, or mils, like that. Now when you divide so that it gives us our answer in moles per liter instead of in moles per mil. So when I divide that number by 1,000, I'm just going to have 1.45 times 10 to the power negative 9 mole per mil. Okay, mole per mil. Okay, now that I've got that, that's the one that I'm now going to use to change to atoms per mil. Okay, so in this case, atoms per mil. So in this case, what do I have? So in this case, the atoms, we said it's that number multiplied by the Avogadro's number. So this number multiplied by the Avogadro's number. Okay, so in this case, what then do we have? Since I already have my 1.45, I'm just multiplying by the Avogadro's number, which is 6.022 times 10 to the power 23 atoms per mole. I'm going to have 8.73 times 10 to the power 23, 10 to the power 14 atoms per mole, or per mil actually, because of the mil there. We just wanted to convert this mole to atoms because that's what they want there. So basically this is how you solve, you know, these questions. Then we come to, during a severe episode of air pollution, the concentration of lead in the air was observed to be dash. Was this dangerous to the health of the people inhaling this air? Explain. Okay, so if we're going to compare the threshold, whether it was dangerous or let me just check. Maybe we're going to use what we written, 8.73. Maybe we might use it. Okay, so let's look at B. During a severe episode of air pollution, the concentration of lead in the air was observed to be that micrograms of lead per cubic meters. Was this dangerous to the health of the people inhaling this air? Explain. Okay, so about explanation, you have to compare dangerous thresholds first. We've been given that it is the dangerous threshold. Have you been given? Okay, I'm trying to Okay, so they've told us 30 micrograms of lead per deciliter of blood poses a significant health risk. So if you've got 30 so it means, well, it's the same question. So we're going to say this is 30 micrograms. It's the one that is very dangerous. Okay, they're saying per deciliter. That's what is there, per deciliter of blood. Okay, poses a healthy risk. So if we're going to convert this one to liters, what is it going to be? You know that a deciliter, they've told us, is 0.1 liters. So I'm going to multiply by the 30 multiplied by the 30 divided by the 0.1 actually, for me to change it to liters. It's going to be 300 micrograms per liter in blood. Okay, this is very dangerous. It poses a significant health risk. That's the dangerous threshold. Now we've been told that the air concentration that was observed is that, okay, 3.01 microgram per cubic meters. So supposed to convert this one to liters to compare. Okay, now if it's 3.01 micrograms per cubic meters, what then is going to be our answer? So it means, you know that cubic in this case, it is multiplied by 10 multiplied by 10 multiplied by 10. That is 1,000 liters. Okay, so because 1,000 liters, I'm going to divide this number by 1,000. So I'm going to have 0.00301 microgram per liter. Now if I compare these two figures, this is 300, this other one is 0.00301. So what then do we conclude? You're able to see that the one that we just calculated is much lower, okay, than the blood risk level itself. So the answer will be it will be a no, because they're asking, was this dangerous to the health of the people inhaling this air? It was no. It was not dangerous. Then the explanation is that the air concentration itself is not direct dangerous compared to the blood threshold that we've been given. So basically that is how we solve this one. Then we come to the other one, which is how many lead atoms will be present in 0.5 liters sample of this air, the approximate lung capacity of the human adult. How many lead atoms would be present in 0.5 liters? Okay, so I don't know if we're going to need this, but let me just rub it. Okay, okay, let's just keep this one just for a while. 0.00301 micrograms per liter. Okay, now how many lead atoms will be present in 0.5? So this is 0.5 liters of air. So now what we have initially, what we have was in the air itself, it was observed that in the air it is 3.01 micrograms of lead per cubic meters. And what to convert this one, it gave us in terms of liters, it gave us 0.0301 microgram per liter. Now the mass of lead in these liters, what is it going to be? Okay, so in this case, what then do? We've been given that how many atoms will be present in 0.5 liters. Okay, this is microgram per liter. What if we put 5 liters or 0.5 liters? What are we going to have? So if in terms of just conversion units, if we say this is 0.00301 micrograms per liter, okay, we're multiplying this by 0.5 actually, 0.5 liters, so that we just find the mass. You're going to realize that since we're multiplying 0.00301 multiplied by 0.5, I'm getting 0.001505 micrograms. Now we're supposed to convert this one to grams. We just check the actual mass. Okay, so what are we going to have? So that is 0.001505 times micro. You know that micro, just the micro itself, it's 10 to the power negative 9, so it is 10 to the power negative 9 grams. Okay, so that is what we have in grams for now. Then we're supposed to convert these grams to moles. Okay, so converting that to moles, what do we have? You know that number of moles is equals to mass over molar mass, right? So now this mass, we divide it by the molar mass for lead. Molar mass for lead is 207.2 grams per mole. So the grams and grams are going to divide. Now the 0.0015, I already have it. 0.001505 times 10 to the power negative 9 divided by 207.02. I'm getting the number of moles to be 7.27 times 10 to the power negative 12. Those are the number of moles. Then now we're supposed to now finally convert the number of moles to atoms, because we've been asked how many lead atoms will be present in that amount. So in this case, what do? We get the same answer, we multiply by the Avogadro's number, right, to find the number of atoms. So in this case here, the number of atoms. So when you get that, we multiply it by 6.022 times 10 to the power 23 atoms per mole. So we're going to have 4.38 times 10 to the power 12 times 10 to the power 12 atoms. So that is what we have in terms of atoms. So that is how we solve this question. So we have about 4. If we're going to round it off, 4.4 times 10 to the power 12 lead atoms in about 0.5 liters of air. Okay, so we come to question number 13. The amino acid methionine, which is essential in human diets, has the molecular formula that determine its molecular mass. Okay, so this is just an introduction to calculations on stoichiometry. So what do we now do to find us the molecular mass? So we got how many? Which atoms do we have? We got C. Those are the atoms. Then what are their masses? Carbon is 12.01. Hydrogen is 1.008. Nitrogen is 14.01. Oxygen is 16. Sulfur is around 32.07. Okay, then how many are there? How many carbon atoms do we have there? We've got 5. I'm going to multiply this by 5. Hydrogen, we've got 11. Nitrogen, we've got 1. Oxygen, we've got 2. Sulfur, we've got 1. Then we just solve. So 12.01 multiplied by 5, that gives me 60.05. Okay, 1.008, 11.09. Then this will be maintained, it's 14.01. Then 16 multiplied by 2, that is a 32. 32.07 multiplied by 1, that is 32.07. Then I'm just supposed to now add all these ones. So 60.05 plus 11.09 plus 14.01 plus 32 plus 32.07. I'm getting 149.22 grams per mole. So that is the molecular mass, 149.2 grams per mole. Okay, then we are taught to, then the second question is asking us the number of moles of hydrogen atoms per, determine the number of moles of hydrogen atoms per mole of methionine. Now this one is it's a very simple question. The formula just showed you that there are 11 hydrogen atoms in this mole, okay, on this molecule. So it means we have, for this one, we've got 11 moles of hydrogen atoms. Why I'm saying 11 is because this in 11 mole of hydrogen atoms, that's what you are going to find per molecule or per 1 mole of methionine. We don't have any stoichiometric coefficient there, so basically it will just be that. Then we come to see the number of grams of carbon per molecule of methionine. Now the number of grams, determine the number of grams of carbon per mole of methionine. So in this case we've already found that what was it? There are 5 of them, and we have to multiply by its mass unit, which was 12. We found that it was 60, right? 60.1 grams of carbon per mole of methionine. It's only 1. There's no coefficient there. So basically that. Then the last one is determine the number of carbon atoms in 9.07 mole of methionine. Now this changes everything because they've now increased the number of moles to 9. Okay, so in this case, what are we going to have? Since 1 mole of a carbon is equals to the same mole of the actual compound itself. So for this other one, we are going to have 9.01 mole of the same methionine multiplied by the 5 moles of carbon. Okay, so in this case, what then do we have? 9 multiplied by 5, that is like, this is 0.7. They've 0.7, this one. 9.07 multiplied by 5, we're going to have 45.35 more. Okay, so that is what we have as the moles of carbon. Now the question is the number of carbon atoms, and you know that number of atoms, we've been finding it, this will just be equals to what you have as the number of moles multiplied by the Avogadro's number, which is Na. In this case, the number of moles we've already found, that is 45.35. Now we are multiplying this by 6.022 times 10 to the power 23. So we're going to get 2.7 times 10 to the power 25 carbon atoms. So basically this is how we solve these questions in this tutorial sheet.